Hello students, welcome to 12th standard physics, second POC physics. Let us start wave optics. Wave optics is a branch of physics which deals with the study of optics, nothing but light instruments, nothing but optical instruments. By considering wave nature of light. Wave nature of light means lambda, wavelength, frequency, phase difference denoted by delta phi, path difference denoted by delta x. So using these parameters we try to understand reflection, refraction, few more phenomena like interference, diffraction, polarization. So in the first topic, in wave optics, let us go through wavefront. Wavefront. If this is a point of disturbance on the surface of water, and if I tap the surface of water at regular intervals like this, then we can see ripples, isn't it? These are ripples on the surface of water. These smooth lines represent locus of all those points which are in phase, which are crest points. Crest, isn't it? This is top view. Top view of ripples of water. Side view, if this point is disturbed, and this is the wave pattern at some instant of time. See, this is crest, this is crest. So this first crest is this. After that there is trough. Trough points are represented by these dotted lines. So crest, trough, trough. After that one more crest, second crest. So this is second crest. So crest, trough, crest, trough. Again I should draw a dotted line. This is crest. So these are called ripples. But in wave optics we call them wavefront. Wavefront. So wavefront is a locus of points which are in phase. If this represents a wave, this is 0, pi, 2 pi, half of pi, pi by 2. This is 3 pi by 2. For time being, a wave is represented by sine function and this represents a wave. Okay. Crest point means this is the crest. For crest, phase is pi by 2. For trough, phase is 3 pi by 2. So these are points which have phase equal to pi by 2. So every point is a crest point, means every point is at pi by 2. Trough means every point is at 3 pi by 2. 3 pi by 2 means trough. Trough. Now, what is a wavefront? Wavefront is locus of points which are vibrating in phase. If this is the point of disturbance, this is a wavefront. Every point, each and every point on this wavefront is at pi by 2 phase. Pi by 2 phase. What is phase difference between any two points in a wavefront? See, phase of this is pi by 2. Phase of this is pi by 2. So difference of these two is 0. Pi by 2 minus pi by 2 equal to 0. So phase difference between any two points on a wavefront is 0. Point of disturbance. This is a wavefront. If this is a wavefront which spreads in space, then let me draw perpendicular at this point. How to draw perpendicular to a circle or a sphere? Draw tangent to the tangent, draw perpendicular. So this is the perpendicular drawn at this point. So this is the direction of propagation of energy. So propagation of energy in a wave is always perpendicular to the wavefront. What is the first point? Phase difference between any two points is 0. Second, the direction of propagation of energy is always perpendicular to the wavefront. Now, if this is the point of disturbance, nothing but source, then from the source, wave is traveling in this direction. So the direction of propagation, of the wave, direction of propagation of the wave is also perpendicular to the wavefront. Propagation of energy is perpendicular to the wavefront. Direction of propagation is also perpendicular to the wavefront. Types of wavefronts. Let this be a point source. Please understand. Point source. This is the source of disturbance. The source of disturbance is the reason for waves, isn't it? Since we are using wave concept, it is better to use source. In this case, point source. This is the point of disturbance. From the point of disturbance, if the disturbance spreads in space, understand, from this point in space, if the disturbance spreads, then it spreads in all directions equally. It spreads in all directions equally means it looks like a sphere. Disturbance from a point source looks like a sphere. If this is a point source, this is the disturbance. After some time, this disturbance spreads. So this will occupy and takes this shape. After some time, this wavefront again spreads. This moves away. Since the disturbance travels equally in all directions. Equally in all directions means that forms a sphere. So what is the nature of wavefront due to a point source means it is spherical. So due to point source, spherical wavefronts. Spherical wavefronts. Okay. On the surface of water, it is 2D, two-dimensional. It looks like concentric circles. Concentric circles. In 3D, they are spheres. In 3D, spheres. Concentric spheres. So the question could be like this. What is the nature of wavefronts due to point source? Answer is, due to point source, the wavefronts are spherical. Now, due to linear source. If this is a linear source means width of this source should be very small compared to length. Okay. This is called a linear source. Due to linear source, if this is the linear source, if disturbance spreads in all directions, then after some time the disturbance looks like this. So the disturbance covers 2 centimeter in this direction means 2 centimeter in all directions means it forms a cylinder. See, this is the linear source. Okay, 2 centimeter in this direction, 2 centimeter in this direction, 2 centimeter in this direction. If you consider 2 centimeter in all directions, then it looks like a cylinder. So this is that cylindrical wavefront. After some time, if this wavefront spreads, nothing but the disturbance spreads, then it looks like one more sphere. This is wavefront after some time. In some more time, if this disturbance travels outward, then this is next cylindrical wavefront. So what is the nature of wavefronts? Due to linear source means, due to linear source, it is cylindrical wavefront. If this is a point source, from the point source we get spherical wavefronts. These are spherical wavefronts, right? This is one more spherical wavefront. Students note, I am not writing complete sphere, okay, not interested. So these are part of spherical wavefronts. As the distance increases, the curvature decreases, isn't it? And if distance is more, then the wavefront almost looks flat. And if I consider small region, this small region looks almost flat, and this is called a plane wavefront. Plane wavefront. So any wavefront at large distance from the source is a plane wavefront, means it looks planar. Point source spherical, linear source cylindrical, but at finite distances. If distance increases and becomes more, then it becomes plane wavefront. Okay. Now observe, this is a point source. From the point source there is a wavefront, spherical wavefront. Let me draw tangent at this point, tangent to this tangent perpendicular. Similarly at this point, tangent perpendicular. From your high school, you know that perpendicular drawn to a tangent of a circle is always along the radius, isn't it? So next, to draw perpendicular at this point, I'll just draw this line along the radius. Now observe, these are rays, diverging rays. Diverging rays. Diverging rays is nothing but spherical wavefront. Spherical wavefront. In our discussion, if we are using spherical wavefront means we are using the laws of or the rules of wave optics. If we are using diverging rays means we are using the laws of or the rules of ray optics. Okay. Similarly, plane wavefront. Simplest case, if this is a point source, here is a lens, and this point source is at the focus, then diverging beam becomes parallel beam, isn't it? That is how we studied in ray optics. There, parallel beam of light converges through a point, or if source is at the focus, then we get a parallel beam of light. Now, if we use such diagrams, then we are making use of ray optics. Rays are drawn. Now, point source. Since it is a point source, spherical wavefront. So these are spherical wavefronts. These are spherical wavefronts. Spherical wavefronts, diverging rays. Parallel beam of light means plane wavefront. Imagine a plane here, one more plane, one more plane. Imagine parallel planes. So these are plane wavefronts. So you are using plane wavefronts means you are using parallel beam of light. Okay, this is how we can visualize wavefronts to rays and rays to wavefront. Now, proof of law of refraction. Law of refraction means the ratio of sine of the angle of incidence to the sine of the angle of refraction is a constant. This is one of the laws of refraction, isn't it? So we have to prove this. Sin I by sin R equal to constant. Let this be an interface. So XY is an interface separating medium 1 and medium 2. This is medium 1, medium 2. Speed of waves in this medium V1. Speed of waves in this medium V2. Waves means light waves. Refractive index of this medium N1. Refractive index of this medium N2. Okay. Let this be a normal drawn at the point of incidence. This is incident parallel beam of light. Incident parallel beam of light. Let me use two extreme rays. This is first ray and this is second ray. Now let me draw perpendicular to these two. So this perpendicular is the wavefront. This is A, B. So AB is an incident plane wavefront. There is a distant source, okay? From the distant source, there is a parallel beam of light. Then those parallel beam of rays or parallel rays are represented by plane wavefronts. Imagine number of planes traveling parallel to each other. So this is one such plane wavefront. So AB is a plane wavefront that is represented by these two rays. So this ray is traveling along A dash A. This is also parallel to this, therefore let this ray incident on the interface at C. This is C. If speed of light in this medium is V1, then speed into time. If V1 is the speed of wave and tau is the time taken by the wave to travel from B to C. See, wave is traveling with some speed V1. Time taken to travel to cover BC is tau. Therefore, distance BC is speed into time. Speed equal to distance by time, distance equal to speed into time. This is V1. Instead of T, let me take tau. Some notation, don't worry about the notation. Tau is time taken by light to travel from B to C. Therefore, BC length is V1 tau. This light ray is traveling, this is also traveling, but this ray has reached the interface, but still this ray is traveling. When the second ray is traveling in the first medium, first ray begins to travel in the other medium. So what I'll do, during this time tau, distance traveled by second ray in this medium. To draw or to trace refracted ray, I should draw an arc. Okay. Look at this length BC. Approximately take half of the length. Diagram looks nice. Please understand, students. To look this diagram proper, let me take half of BC. So keeping half of BC as radius, let me construct an arc. So this is the arc drawn centered at A. Now let me draw tangent plane from point C to this arc tangent. Tangent means straight line which touches at only one point. So this is the tangent plane. In 3D it is a plane. So this plane touches this arc at this point. Now let me join A and this point. Students, are you surprised? See here, incident ray. This is the refracted ray. This point is E. A, B, C, E. AE is V2 tau. Understand? V2 tau. During this time tau, when light wave is traveling with velocity v1, it covers BC. With velocity v2, distance traveled in tau is this. I can make it longer or shorter than this, just to represent the wave is traveling with other velocity. Okay. Suppose from B, a guy is covering 10 meter in 2 seconds. Okay, 2 seconds, 10 meter. Whereas in the other medium, in 2 seconds, let that guy travel with 5 meter. I hope you understood this. In this medium, 10 meter in 2 seconds, this length. In the other medium, in 2 seconds, distance traveled is 5 meter. That is why I have decreased the length. I can also increase, doesn't matter. Okay. Now AE is the refracted ray. CE is the refracted wavefront. AB is the incident wavefront. CE is the refracted wavefront. A dash A is incident ray. AE is refracted ray. If this is the incident wavefront, angle between incident wavefront and the interface is the angle of incidence, I. If this is I, then this is 90 minus I and this angle is I. Again you are surprised, isn't it? Angle between incident wavefront and the interface is I. Then this angle is also I. That is why angle between normal drawn and the incident ray is taken as the angle of incidence. So you had a question in ray optics, right? Why this angle is taken as angle of incidence? Now here is the answer. Similarly, refracted wavefront. Therefore, this angle is R, angle of refraction. If this is R, this angle is 90 degree. Then this is 90 minus R. If this is 90 minus r, then this angle is r. So r is angle of refraction. This is normal. With little practice, you can draw beautiful diagrams. Okay. Make sure that you don't spend more time on the diagram. But writing, don't spend more time. But to understand, spend more time. Now, all these things I should write here. Let xy be the interface of medium 1 and medium 2. That is this. Let v1 and v2 be the speeds in medium 1 and medium 2 respectively. Consider a plane wavefront AB traveling along A dash A. Consider a plane wavefront AB traveling along A dash A is incident on the interface at an angle of incidence I. Let tau be the time taken by the wavefront to cover the distance BC. Therefore, BC equal to V1 times tau. During this time tau, the refracted wavefront travels a distance V2 tau. That is this length. To determine this wavefront CE, an arc is drawn. What should be the radius of the arc? V2 tau, centered at A. V2 tau is drawn centered at A. The tangent plane CE represents the refracted ray and AE is the CE is the refracted wavefront. Again, the tangent plane CE represents the refracted wavefront and AE represents the refracted ray. So this is the refracted ray. And angle between refracted wavefront and the interface, that is this angle, is the angle of refraction. If this is R, this is 90 minus R, then for this angle is R, that is this angle is R. In triangle ABC, sin I equal to, in triangle ABC, sin I equal to opposite side BC by hypotenuse is AC, because this is 90 degree, therefore AC is the hypotenuse. So BC by AC. Length BC is V1 tau by AC is the hypotenuse AC. Similarly, in triangle ACE, let me consider sin R. If this is R, sin R is opposite side AE by hypotenuse. Hypotenuse is AC. AE is V2 tau. AC is AC. Now let me consider sin I by sin R. Okay. Sin I V1 tau by AC, sin R V2 tau by AC. AC get cancels, tau get cancels, V1 by V2. Observe, sin I by sin R equal to ratio of two constants V1, V2. Ratio of two constants is also a constant. So ratio of sine of the angle of incidence to sine of the angle of refraction is a constant for a pair of media. So this is Snell's law. This is law of refraction. Now different cases. If V1 greater than V2 implies, understand, V1 greater than V2, numerator is greater than denominator means sin I must be greater than sin R, implies I must be greater than R. I greater than R. I greater than R means this is the interface, this is normal drawn at the point of interface, at the point of incidence. I is greater. If this is the incident ray, I, angle of incidence, greater than R means the refracted ray should be bent towards the normal. So this is R. This is true only when V1 is greater than V2. This is V1, this is V2. V1 greater, speed of light is more means it should be rarer medium. And this is denser medium. This is what we learnt in ray optics, isn't it? When a ray of light travels from rarer medium to denser medium, after refraction, the ray bends towards the normal. That is I greater than R. Second case, let me write these things in statement. Okay. If ray is traveling from a region of higher speed to a region of lower speed, nothing but rarer medium to denser medium, it bends towards the normal. Now let us discuss second case where V1 is less than V2. V1 less than V2. Speed is less means denser medium, rarer medium. Implies, see here, V1 less means numerator is less. Sin I should be less. Nothing but I should be less than R. It bends away from the normal. If light is traveling from a region of lower speed to a region of higher speed, lower speed means denser, higher means rarer, denser to rarer, it bends away from the normal. Let us check this. This is the incident, this is the interface, normal. Let this be the incident ray. medium 1, medium 2. This is denser medium, rarer medium. Angle of incidence should be less than angle of refraction. So angle of refraction should be more. Look at this, R. R is greater than I. So naturally, the ray after refraction bends away from the normal. That is this point. We have studied this in ray optics, isn't it? Now we have proved it. Next point. If C is speed of light in vacuum, then refractive index of first medium is C by V1. Refractive index of second medium is C by V2. C by V1, therefore what is V1? V1 equal to C by N1 and V2 equal to C by N2. I want V1 by V2. Now V1 by V2 is C by N1. V2 is C by N2. C get cancels. This N2 goes to numerator. Now sin I by sin R, which is V1 by V2, we proved this, equal to, see, V1 by V2 is N2 by N1. N2 by N1 implies N1 sin I, cross multiply, N1 sin I equal to N2 sin R. So this is Snell's law in general form. Snell's law in general form. Next point. In the diagram, in this diagram, if BC is one wavelength, if length BC is one wavelength is lambda 1, medium 1, therefore wavelength in this medium is lambda 1 and wavelength in the other medium lambda 2. AE is lambda 2. When this one wave is generated, during that time one wave is generated in the second medium, that is lambda 2 with wavelength lambda 2. Then lambda 1 by lambda 2 equal to BC by AE. And what is BC by AE? V1 tau by V2 tau. BC is V1 tau. This is V2 tau. Tau tau get cancels. Therefore, lambda 1 by lambda 2 equal to V1 by V2. Or let me rearrange. V1 by lambda 1 equal to, let me take V2 to the other side, V2 by lambda 2, or velocity or speed by wavelength is frequency. Frequency of waves in first medium equal to frequency of waves in second medium. And what do you mean by this? When light travels from one medium to another medium, speed changes, wavelength changes, but frequency remains same. but frequency remains constant. Now second derivation, proof of law of reflection using Huygens principle. Okay, let this be an interface, actually a reflecting surface, since it is law of reflection, reflecting surface, a mirror. I should shade the other side. For time being, let me manage with a line. Okay, this is a mirror, upper surface is the reflecting surface. This is normal drawn at the point of incidence. These two are parallel rays. So these two rays are traveling along A dash A. Perpendicular drawn to this is a wavefront. So let me draw perpendicular. This is the wavefront. So A, B is the wavefront. Consider a plane wavefront AB traveling along A dash A, incident on the reflecting surface. Angle between incident wavefront and the reflecting surface is the angle of incidence. So this is the angle of incidence I. See, these two rays are traveling. This ray is incident on the reflecting surface, but still this ray is traveling. By the time the second ray covers BC, first one will retrace. First one will get reflected. Now, to draw the reflected wavefront and the ray, what we should do? If v is speed of wave in this medium and tau is the time taken by the wave to cover BC, then speed into time is the distance BC. During this time, distance traveled from A should be Vt, because reflection takes place in the same medium. So keeping Vt as reference, I should draw an arc. So keeping BC as radius, an arc is drawn. Now from C, I should draw a tangent plane, a tangent. And this is the reflected ray. A, and this point is E. Let me draw the arc with different color. So this is the arc. AE is the radius. This AE equal to BC. So AB is the incident wavefront, whereas CE is the reflected wavefront. Something like this. If this is the incident wavefront, something like this. If this is the incident wavefront, observe already part of the wavefront is hitting the reflecting surface, whereas this part of the wavefront is still traveling in air. When this portion is still traveling in air, this gets reflected, something like this, and then the reflected wavefront. So CE is the reflected wavefront. This is angle of reflection 90. If this is 90, this is R, angle of reflection R. If this is R and this is 90, then this is 90 minus R, and this angle is R. Angle of reflection, angle of reflection. Angle of incidence, if this is I, this angle is 90 degree, therefore this angle should be equal to I. This is angle of incidence, angle of reflection. Now this is 90 degree, this angle is also 90. This length equal to this length. AC is common to both. Therefore these two triangles AEC and ABC, these two are congruent triangles. Therefore these two angles should be there, equal. That is BAC equal to ECA. BAC is angle of incidence, ECA is angle of reflection. This is nothing but the law of reflection, isn't it? Angle of incidence is equal to angle of reflection. Now let me shade the reflecting surface. Let me shade the mirror. Upper surface is reflecting, therefore shading should be on the other side. Now let me write statements. Consider a plane wavefront AB traveling along A'(A) incident on the reflecting surface. Let tau be the time taken by the wavefront to travel the distance BC. Therefore BC equal to V into tau. V into tau. During this time tau, light is reflected from A. And distance traveled by light from A is also equal to Vt. The reflected wavefront also travels the distance V tau. To determine the reflected wavefront, an arc of radius V tau is drawn centered at A. That is this arc. The tangent plane CE represents the reflected wavefront. And AE is the reflected ray. Let R be the angle of reflection, angle between reflected wavefront and the reflecting surface. Therefore, length BC equal to AE equal to V tau. AEC and ABC are congruent triangles. Implies these two angles should be same. This angle is BAC and this angle is ECA. So angle ECA should be equal to BAC. ECA. ECA is angle of reflection equal to angle of incidence. So this is law of reflection. Angle of incidence is equal to the angle of reflection. Students, the proof of law of reflection and the law of refraction are for 3 marks. Please copy the diagram and copy all the steps. Write twice or thrice and practice. Okay? A small topic, Doppler effect. This is a source. The source is emitting waves. These are the waves. And this is the observer. If there is relative motion between source and the observer, then frequency heard by observer is different from the actual frequency nu. Source is emitting frequency nu, but observer observes some other frequency. So this change in frequency due to relative motion between source and the observer is called Doppler effect. And the expression for Doppler effect, change in frequency by original frequency. This is fractional change in frequency is equal to minus, this is velocity, radial velocity, by speed of light, c. This is the expression. Radial velocity means velocity of the observer along the radius. Suppose this is the source. Observer is moving like this. This is velocity of the observer. At this point, draw radius. You should find the component of this velocity along this radius. Students, how to find component? Drop a perpendicular. This is the component. In last year, motion in a plane chapter, you have studied about components of a vector. To find components, you have to drop a perpendicular. So this angle is 90. This is V radial. Radial component of velocity. If observer is moving, then find out component of that velocity along the radius. Okay. And as a convention, if source is moving away from the observer, this is source, this is the observer, source is moving away from the observer, then this radial component of velocity is taken with positive sign. Away positive, towards negative, because velocity is a vector quantity. If direction is reversed, then sign also gets reversed. First case, if this is the observer and source is moving away from the observer, then frequency decreases. Frequency observed by the observer decreases. Second case, this is the observer. If source is moving towards the observer, then frequency increases. Frequency decreases means, in astronomy this is also called red shift. Red shift refers to the source moving away from us. So we are the observers, isn't it? So this is called blue shift. Blue shift, source moving towards. Red shift, moving away. Huygens principle. This is a way to imagine how the propagation of wavefront takes place. If this is a source, from the source, these are the wavefronts. So the wavefronts spread in space. How do they spread in space? That was explained by Heigens principle. So Huygen said, if this is a source and then this is part of a wavefront or wavefront, he said every point on the wavefront behaves like secondary source of disturbance. So from every point disturbance spreads. Every point disturbance spreads means these are the disturbances, and these tiny disturbances from every point are called secondary wavelet. Piglet, wavelet, leaflet. So these are tiny waves. If you consider forward envelope of all these wavelets, then that represents the next wavefront. So how wavefront travels from this point, this place to this place means we have to visualize all these tiny wavelets, and common tangent to all these tiny wavelets gives the secondary, the next wavefront. See, these secondary wavelets travel in the outward direction. They also travel in the inward direction. So Huygen simply said, don't consider backward motion of the wavelets. He said the amplitude of this backward wavelets is almost zero, and there is maximum amplitude in the forward direction. So this is something unusual which he couldn't explain. He simply said, consider this and you will be able to locate the next wavefront. So this is ad hoc assumption of Huygen. Ad hoc assumption means there is no proper logic in this. There is no formal proof for this. So go through this statement for Huygens principle. Each point on the wavefront is the source of secondary disturbance, and the wavelets emerging from these points spread out in all directions with equal speeds. These tiny wavefronts are referred as secondary wavelets, and the common tangent to all these spheres, we get new position of the wavefront, that is this red, new position of the wavefront at a later time. If this is this wavefront arises, after some time the new wavefront arises. So that is why the term later time. Okay.